everyone, welcome to a new episode of the Bio-Inorganic Chemistry course. In this module, we are going to learn the dioxygen carrying protein hemoglobin in detail. In this module, we will learn about the structure of hemoglobin. We will understand the role of polypeptide chain in hemoglobin, and also we will understand the concept of cooperativity and Bohr effect. Now we are moving on to the structure of hemoglobin. Here you can see the structure of hemoglobin in a glance. Hemoglobin is a tetramer weighing about 65 kilodaltons. Here you can see the hemoglobin protein, and you can see there is a heme, which is a prosthetic group that is present in hemoglobin. So this is shown here and it is enlarged here. This is the heme group. You have already learned about heme in the lower classes and in the previous lectures. Heme is the integral part of hemoglobin molecule. It also contains homologous globulin chains which are connected together by disulfide bridges. The adult hemoglobin molecule contains about 2 alpha globulin chains which comprise of 141 amino acids and 2 beta globulin chains which consist of 146 amino acid groups. That is, you can see here it is a tetramer, that is, it is having 4 units, 2 alpha chains and 2 beta chains. The 2 alpha chains, that is the 2 alpha globulin chains, the 2 alpha globulin chains consist of about 141 amino acids, and the 2 beta chains, here you can see the 2 beta chains, it consists of about 146 amino acids. In the tetramer structure, we have also got 4 heme units. Here you can see there are also 4 heme units. This is the heme unit. We have 4 heme units, or the 4 active centers of hemoglobin, which is wrapped outside by the protein chain. The globulin chain is being attached to the 4-ion porphyrin complex known as heme. You know that the heme contains the porphyrin ring system. The porphyrin ring system contains iron 2 plus in the center, and you have 4 pyrrole ring systems. The heme group has iron atom held at the center, and it is having, or it is connected to 4 nitrogen atoms from the pyrrole ring system, which is called porphyrin. It contains 4 iron atoms, as it is a tetramer, it has 4 subunits, and hence it has 4 iron atoms in it. It is the iron that is contained in the hemoglobin that accounts for the red coloration of blood. Now we are going to learn about deoxyhemoglobin, that is, before coordinating with oxygen, it is called deoxyhemoglobin. The coordination number of ferrous ion in deoxyhemoglobin, that is before coordinating with oxygen, is actually 5, and it is having a square pyramidal geometry. Deoxyhemoglobin possesses a square pyramidal geometry and it has 5 coordination. We know that the ferrous ion is coordinated to 4 nitrogen atoms from the pyrrole ring system, and we have one imidazole nitrogen from the histidine residue that is connected to the polypeptide chain. This histidine is known as proximal histidine. The histidine that is coordinated in the 5th coordination site, that is the 4th coordination is occupied by the 4 nitrogens of the pyrrole group, and we have another nitrogen that is from the amino acid histidine. The imidazole nitrogen of the histidine residue is coordinating in the 5th position, and that histidine is known as the proximal histidine. We have already learned about the proximal histidine in myoglobin in the previous lecture. And this proximal histidine is the residue 92 of the beta chain and residue 87 of the alpha chain of the hemoglobin. The side of the heme plane at which the exchangeable ligands are bound is called the distal side. That is, in the distal side, the ligands are not actually connected or coordinated. That is where the exchangeable ligands are present, and it is known as the distal side. In deoxyhemoglobin, that the 6th coordination site is actually vacant. The distal side has a histidine residue called the distal histidine, which is near the heme but clearly not bound to it. In the last lecture in myoglobin, we already learned about the distal histidine and proximal histidine. The proximal histidine is being bonded to the iron atom, while the distal histidine is not bound to the iron atom, but it is present in its vicinity. It makes the 6th coordination site of deoxyhemoglobin accessible to only small molecules. That is, since the distal histidine is present near the 6th coordination site, large molecules cannot access the iron center. It only will access the small molecules. The protons present in the heme cavity weaken the iron to oxygen bond in oxyhemoglobin. Now let us see the oxidation state of iron in deoxyhemoglobin. We have iron in the +2 oxidation state in deoxyhemoglobin, and it is in the high spin form. The high spin ferrous ion is almost 78 picometer and is larger in size than the heme cavity. So what happens? It will lie approximately 40 picometer out of the heme plane in the or towards the proximal side, giving a dome shape to heme. That means that the high spin ferrous ion cannot sit into the cavity of the heme. It is therefore a bit above the heme plane, as its size is quite larger. That is, we are not having a planar structure, that is Fe2 plus is not present in the cavity but above the plane of the porphyrin ring. Now let us see the structure of oxyhemoglobin. We know that the dioxygen molecule binds reversibly to the Fe2 plus at an angle 120 degree, and this will bring about conformational changes in hemoglobin. That is, when Fe2 plus molecule in the high spin state is getting oxygenated, that is, the oxygen is being coordinated to the Fe2 plus, what will happen? It will cause the conformational changes in the around the hemoglobin protein chain. Here the spin state of Fe2 plus will change from high spin to low spin. Very important. Upon oxygenation, the deoxyhemoglobin will get converted into oxyhemoglobin. Here the Fe2 plus gets converted from high spin state to the low spin state. So after this, it will decrease in size. That is, when the iron atom or ion Fe2 plus is getting changed from the ion high spin to low spin, it will reduce its size and it will be capable of sitting inside the cavity and will come to the plane. The ferrous ion will sit beautifully inside the heme cavity upon this transformation, and it slips into the heme cavity, and it also pulls the proximal histidine towards the heme plane. Thus, the Fe2 plus is now hexacoordinated in oxyhemoglobin or the oxygenated hemoglobin, and it now has a octahedral geometry. Oxygen is hydrogen bonded to the imidazole NH of the distal histidine at this point, that is of the oxyhemoglobin. Now, let us move to the role of polypeptide chain in hemoglobin. So, what happens when oxygenation occurs to the polypeptide chain? What is the conformational change occurring? That is what we are going to see next. The polypeptide chain in hemoglobin, that is the globular chains, will function as the carrier of heme. It has the property to stabilize the heme oxygen complex. It has the property to stabilize the heme oxygen complex so that the oxidation of Fe2 plus of heme does not occur. So, that is very important. That is, the protein chain globin will protect or stabilize the heme oxygen complex, and it will prevent the oxidation of Fe2 plus to Fe3 plus. The polypeptide chain, we know its alpha and beta are folded in a way that the hydrophobic residues are inside and the polar residues are actually outside. The hydrophobic residues in which the heme is present. So, it is also responsible for the formation of heme pocket where the Fe2 plus or where the heme is present. It also helps in preventing the irreversible dioxygen oxidation in two ways. Let us see how it is preventing. For the oxidation of Fe2 to Fe3, the simultaneous presence of oxygen and one or more molecules of water is required. So, what the globular chains will do is that the residues in the heme pocket have hydrocarbon groups, that is the non-polar group. They provide the hydrocarbon environment and it will act as a non-polar solvent extruding the water molecule out of the heme pocket. So, it will not allow the water molecules to come and attach in the heme pocket, and thus it will prevent the oxidation of iron 2 plus to iron 3 plus. So, because of the presence of this polypeptide chain, the formation of the mu oxoheme dimer becomes sterically unfavorable. Now, we move on to the next part, that is the electronic state of iron and oxygen in oxyhemoglobin. So, the molecule of oxyhemoglobin is found to have zero magnetic moment, that is, it does not have any unpaired electrons or the spin is 0. So, in order to explain this, two hypotheses were proposed, one by Pauling and Correll and the other by Weiss. First, let us see the Pauling and Correll hypothesis. The hypothesis says that the oxyhemoglobin is actually diamagnetic in nature. So, here what happens is that the iron 2 plus is present in the low spin state and is coordinated to the singlet oxygen. So, both the species are present in the diamagnetic form. You can see iron 2 plus, that is iron 2 plus D6 is having 6 electrons and they are found in the low spin. So, the T2G orbital is completely filled and it is spin paired. So, this is diamagnetic. Now, the singlet oxygen, that is the bound oxygen, is also diamagnetic. That means there is no unpaired electron. So, the spin is equal to 0. This is the Pauling-Correll hypothesis. Now, let us see what is the Weiss hypothesis. So, oxyhemoglobin is present in low spin iron 3 state, that is the low spin iron 3 state is actually having a spin of half, and also the superoxide radical anion, that is O2 minus, is also having the spin half. So, the ion exists in the +3 oxidation state, lost spin state, and oxygen in the as the superoxide radical form. So, what happens is that these species are formed by electron transfer from Fe2 plus to the oxygen. Here what happens is that there is strong antiferromagnetic coupling occurring between the low spin Fe3 plus and the oxygen superoxide radical, and hence due to the strong antiferromagnetic coupling, it is observing diamagnetism at room temperature. You can see here Fe3 is D5 low spin, you have one unpaired electron. Here this is the superoxide radical, it is also having radical anion is having another unpaired electron, and this two will couple and it will become diamagnetic at room temperature. Now we are going to see the chemistry of oxygen binding and transport. So, dioxygen binding to one heme site causes a spin state change from high spin to low spin. That is, the deoxyhemoglobin is present or is having ion in the +2 oxidation state, and this ion 2 plus is present in high spin, and when oxygen is binding to Fe2 plus high spin, it gets converted to low spin. After this, ion moves into the porphyrin cavity of the oxyhemoglobin. The proximal base will also move along with the ion. Now, the proximal base will drag the F helix along with it, and this induces a large protein conformational change which is reflected in the cooperativity. Now, let us see what is the cooperativity effect in hemoglobin. We already know that hemoglobin is a tetramer that contains 4 different heme units, and each of heme unit is capable of binding oxygen molecules, and we can bind a maximum of 4 oxygen molecules. Suppose K1, K2, K3 and K4 are the stepwise formation constants for the binding of oxygen in the hemoglobin molecule. It is observed that the stepwise stability constant follows the order
K1 less than K2 less than K3 less than K4.
That is, the K4 is having the highest stability constant. This is quite different when Fe2 plus, or it is not found in the tetramer form, or when the Fe2 plus site is independent. So, what this order says is that is the K4 or the last stability constant is greater than the first, second and third. It means that the binding of the first oxygen is the most difficult one, and the fourth oxygen molecule binding is actually very easy and it happens more readily and tightly. So, binding of this dioxygen molecule to hemoglobin enhances the further binding of additional dioxygen to the same hemoglobin molecule. This effect is known as cooperativity, that is, the binding of one dioxygen molecule to hemoglobin will further enhance the capacity to bind the further oxygen molecules. Similarly, the removal of one dioxygen will make the removal of other dioxygen molecules easier, and this phenomenon is known as cooperative effect. Here you can see the K1 stability constant is only about 5 to 60, but the K4 is very high compared to K1, that is about 3000 to 6000. So, the binding of the first step, that is the binding of one oxygen molecule is the difficult step. Here you can see that the K4, this binding of one oxygen molecule will trigger the further addition of other oxygen molecules. So, I already mentioned that in the statistical point of view, the order of the stepwise stability constants should be K1 greater than, K2 greater than, K3 greater than K4. So, in this case, what is the situation? There is no interaction through the protein chains between the two ion centers or between two different heme centers in the same molecule. There is no interaction through the protein chain.
Or else we can say that the heme centers are isolated.
But actually in hemoglobin, it follows the reverse order, which means that heme centers in hemoglobin are not isolated, or the Fe2 plus or the heme centers are not isolated or free. They are actually linked with the protein chain, and this influences the stability constant and they control the reactivity. So, the protein molecule has a great role to play for the oxygenation of hemoglobin. Now, let us see the oxygen dissociation curve for hemoglobin. So, what is oxygen dissociation curve? It is also known as saturation curve. It is the plot of percentage saturation with dioxygen versus the partial pressure of oxygen. The percentage saturation of oxygen we are plotting in the y-axis and versus the partial pressure of oxygen in the x-axis. It is observed that the hemoglobin dissociation curve is actually sigmoidal for hemoglobin. It is sigmoidal curve. So, what does it mean? It means that at lower partial pressures of oxygen, hemoglobin does not bind to oxygen effectively. At low partial pressure of oxygen, hemoglobin does not bind to oxygen effectively. But at higher partial pressure of oxygen, hemoglobin will bind to oxygen very effectively. That is what the oxygen dissociation curve shows. Now, let us see how the oxygen transport is happening between the lungs and tissues. It can be explained with the oxygen dissociation curve. It helps to understand how the blood is carried from, how the blood carries dioxygen from the lungs to tissues. We know that in the lungs, partial pressure of oxygen is very high. When we inhale, our lungs will become filled with oxygen and the partial pressure of oxygen is very high in the lungs, and hemoglobin will get saturated with dioxygen. When we go to the tissues, what happens? The partial pressure of oxygen is very low in the tissues. Hence, the affinity of hemoglobin for oxygen is low and it releases the bound oxygen. So, that is how the oxygen is transported between the lungs and tissues. Now, let us see what is a Hill plot. The binding of dioxygen to hemoglobin can be described by this plot. Okay, the binding of dioxygen to hemoglobin can be described by this plot. Consider the equilibrium. Hemoglobin plus n number of oxygen gives the bound hemoglobin oxygen n numbers. The equilibrium constant for the above equation can be given as beta. It is given by HbO2, that is the bound form, n times divided by concentration of hemoglobin and the number of oxygen molecules, that is the concentration of oxygen, where the concentration of the bound hemoglobin to oxygen is the concentration of oxyhemoglobin and Hb is the concentration of deoxyhemoglobin and oxygen is the concentration of the uncombined oxygen. The plot of log y by 1 minus y versus log partial pressure of oxygen is actually the Hill's plot. So, the y is given by concentration of the bound hemoglobin divided by hemoglobin total, and the slope of it is called Hill's coefficient. It is actually the measure of degree of cooperative binding, that is the n gives the degree of cooperative binding and is called the Hill's coefficient. The degree of cooperativity will increase with the value of n. So, if we have a higher value of n, it means that there is greater degree of cooperativity. The hemoglobin has an n value approximately equal to 2.8. This shows that binding of oxygen in hemoglobin is cooperative. If oxygen is bound independently to the 4 heme units, its value could be 1. Okay, that means if the heme centers were free and not bound, its value could have been 1. But since it is bound to the protein chain, it is having greater cooperativity, or the cooperativity effect is prominent, and it has an increased value of N, that is 2.8. Next, we will see the molecular basis of cooperativity. We know that hemoglobin has a quaternary structure. It can exist in 2 quaternary states, namely the T state, which is the tense state, and the R state, that is the relaxed state. Conformations of individual polypeptide chains and the relative orientations are different for the both states, that is the T state and the R state. The oxygenation rotates the alpha 1 beta 1 dimer in relation to the alpha 2 beta 2 dimer about 15 degree. When hemoglobin switches from the T state to the R state, alpha 1 and alpha 2 globins move closer to each other. Similarly, the beta 1 and beta 2 globins also will move closer to each other in the R state. The 2 states are actually in equilibrium with one another. The dioxygen can bind to hemoglobin in both the states. However, it has a higher affinity for hemoglobin in the R state. Please remember that the affinity to dioxygen for hemoglobin in the R state is actually greater. The deoxyhemoglobin is constrained by salt bridges, or the electrostatic interactions between the polypeptide chains in the 4 heme subunits. There are actually 8 salt linkages,
2 linkages between beta units,
and 4 salt linkages between the alpha units, and 1 each between the alpha and beta units. Here you can see the tense state and the R state, the alpha chains and the beta chains. The chemistry of this oxygenation of hemoglobin can be explained by the Peruch's mechanism. This is a trickle mechanism that will explain the basis of cooperativity in hemoglobin. So, on oxygenation, what will happen? The ferrous ion will get changed from the high spin state to the low spin state, and it will become smaller in size, and it will be capable to fit in the heme cavity. As it is bound to the proximal histidine, it also pulls the proximal histidine towards the plane of the ring. This movement of proximal histidine leads to change in the tertiary structure of the polypeptide chain of the subunit. That is, the movement of the proximal histidine to the cavity, towards the cavity, will change the entire tertiary structure of the polypeptide chain of the subunit. This conformational changes lead to the rupture of some of the salt linkages between the subunits, and the strain of hemoglobin molecule will get further reduced. This encourages the binding of oxygen to the ion of the second heme unit, which in turn encourages the binding of oxygen to the third and then to the fourth heme unit. Or the strain of the hemoglobin is reduced by the rupture of the salt linkages, and it will encourage the binding of oxygen molecule further. This sequential increase of oxygen affinity gives rise to the sigmoidal shape of oxygen dissociation curve in hemoglobin. Now we are going to see another interesting effect of the oxygenation, that is the Bohr effect. As the name suggests, you know that there is some relationship with Bohr. We know Niels Bohr. Actually, Christian Bohr is the person who observed this Bohr effect, and he is the father of Niels Bohr. He observed that the increased concentration of protons or carbon dioxide will reduce the oxygen affinity to hemoglobin. He observed that the increased concentration of the protons or carbon dioxide will reduce the oxygen affinity of hemoglobin. The chemical basis for the Bohr effect is due to the formation of the bridge of the quaternary structure. The salt bridge interactions between the two amino acid, this amine group and the acid group, they have these interactions in terms of hydrogen bonding. So, what is Bohr effect? Simply we can say that it is the dependence of the affinity of hemoglobin for oxygen on pH. The change in pH will break some of the salt bridge interactions, and Bohr effect is significant for transporting oxygen from hemoglobin to myoglobin. The transport of hemoglobin from the transport of oxygen from hemoglobin to myoglobin can be explained by Bohr effect. Bohr effect is simply the dependence of the affinity of hemoglobin for oxygen on pH. Here you can see a graph. It shows the change of oxygen affinity with pH. We can see that the percent of oxygen saturation versus the partial pressure of oxygen is plotted here. The myoglobin curve is actually hyperbolic, and this nature of the curve is due to the fact that it has greater affinity for oxygen at lower partial pressures. That is, it is having low affinity to oxygen, it is having greater affinity to oxygen at low partial pressure of oxygen. In contrast, our hemoglobin is having a sigmoidal shaped curve. That means that it has greater affinity to oxygen at greater partial pressure of oxygen. This shows the change in oxygen affinity with pH. You can see the variation of oxygen affinity with pH here, that is the Bohr effect. So, the affinity towards dioxygen decreases as pH decreases. Due to the absence of cooperative interaction in myoglobin, there is only one subunit in myoglobin, and hence it does not show Bohr effect. Oxygenation is favored in basic condition, that is by hemoglobin. That is, the basic condition will favor oxygenation in hemoglobin due to the elimination of hydrogen bonding, whereas the deoxygenation is favored in acidic condition. At low partial pressure and greater acidity, like in the venous blood or our muscle tissue, after rigorous exercise, the hemoglobin will have low affinity to oxygen. This low affinity enables hemoglobin to transfer its oxygen to the muscles, that is to the myoglobin. As the pressure increases, so does the affinity of hemoglobin for oxygen, and as a result, hemoglobin can pick up oxygen in the lungs. In this module, we have learned about the structure of hemoglobin, the mechanism of oxygen transport in hemoglobin, particularly the cooperative effect, Bohr effect, and the Perutz mechanism. I hope you have benefited from this lecture and you have understood the role of hemoglobin in oxygen transport in human body. Thank you.